Hello, my name is Rowan Primrose from Equip Design and Consulting, based in Sydney, Australia. This is my first video session, but looking at tips and tricks for CAD modelling, predominantly in Creo, a little bit of SolidWorks, and also other tips and tricks for industrial design and engineering. Today I thought I'd start with one that I've done a couple of times live, but it's top-down design using skeletons in Creo. And give you tips and tricks on line, running through the base, but getting uniform matching across the different parts to ensure that your product is going to come out the way you intend it. You can see here we've got multiple parts. It's mainly a skin model based on a mouse that I had at the time. There's not many straight surfaces in it, which was the design trend at the time. Everything was very organic. Certainly the modern CAD packages allow for that, but certainly top-down design using skeletons is a fantastic tool to be able to control those parts as you sort of slice up the overall shape into the subcomponents. You can see here we've got the top case or top fascia. You've got the top case with an overmolded part, then you've got your bottom case assembly, which is made up of a main housing and then a battery cover, and then you've got your little non-friction feet and a bit of a wheel. If we do a quick exploded view, you can see the level of complexity of the part lines as those come together and the general layout of the parts. Certainly this is an external model, but you can use these top-down design techniques to integrate skinning external covers around internal chassis or frames or mechanical architecture. Imagine this one would have a PCB in it, some batteries, and some other sort of engineering components. In terms of the structure of how we model using top-down design, looking at the model tree here, it's broken up into your main assembly. You've got your upper body. You've got your main body there, which is two parts: a substrate with an overmold, which is those two components there, the main body and the main body overmold. Now we go further down the model tree, you've got your mouse wheel, which on a fully modelled part would have some mechanical interaction with components on the inside, and then you've got your lower housing, which is made up of two sub-assemblies, each with a plastic housing, and then the little feet just allow the mouse to slide across the table. In terms of top-down design, in Creo we call them skeletons. In SolidWorks we call them start parts, or other programs call them master models. So this is one defining part. It doesn't have to sit up the model tree, but certainly I like having it there because it just gives us that hierarchy of how the assembly is sort of structured and created. So if you're coming to use someone else's model, or someone's taking up one of my models or assemblies, they can see that structure and how the architecture is put together, and also how that sort of reflects down through the references. In terms of skeletons, I try to keep them fairly lightweight. So this one only has sort of planes, axes, curves and surfaces or quilts to control them. I try not to use solids, just to keep them fairly lightweight for sort of transferring data around and trying to sort of minimize the impact on your servers to keep your IT guys happy. So this model here, you can see a couple of hidden curves there. This is just the general sort of construction features that went together to make up this mouse model, and then these surfaces are what constrains the the starting geometry for each of the parts. Main body surfaces are these ones here, which control the shape, and then we've got a couple of these bounded blends through here, which will control that one's actually an extrude, which control the part line between the parts. The advantage of this is you can controlling the part line at the top level. So for this part line here between the top fascia and the top body, it's constrained at this part. So if we make a change at this level, it will then filter down, and I'll get to that a bit later on how we go through that. Certainly in Creo, once we've constructed up our model, it's kind of, or when we are constructing up our model, it's kind of looking into the crystal ball where you need to have an idea of where you're going so you can model on how to get there. Certainly, it's good to start your skeleton model and then filter the references down into the parts. But then you can, it's a sort of backwards and forwards, a sort of continual process of updating your skeleton, filtering those references down to your parts. And as your design develops, you'll be going back to your skeleton and then back to your parts, back to your skeleton, back to your parts. The way we do that is through these published geometries. So once we've got our majority of our geometry defined, doesn't have to be totally defined, but certainly defined enough to give us our forms and our shapes of our parts. We know how we're going to carve up each of those parts. Then this published geometry feature is where we capture parcels or a bundle of features that are pertinent to that particular part. So here we start with one of the simpler ones, the wheel. The geometry, which really is constraining that wheel within assembly, this is a very simplified look at it, is the rotation of the wheel shape and then the axis of which it's aligned to. If we go and do an edit definition of that wheel, we've picked the surfaces and then we've picked the axis and then the front plane and the top plane, which go to define that part. Similarly with the upper body, these are the surfaces that go to define that upper body and also that upper fascia part. You notice that we don't select any of the bottom features here below this part line because those features just aren't relevant to that part, so we don't want to filter them down and sort of have extraneous surfaces that we need to then go and turn off in a lower part, or if someone comes into a model, you get every surface. So one fantastic benefit of Creo with published geometries is we're just selecting those geometries and those features that are going to relate to that part to keep that part as lightweight as possible, and also makes it very clear when you go and look at a new part or someone else's part that's modeled up, you can really see which references from which skeleton geometries are driving those parts. If we go and have a look again at the bottom, you got your main body there, and then you got your lower body, which is just looking at those bottom ones. The references from the main body really aren't related to the wheel at all, so they're not included in that external published geometry parcel. If we go back to our mouse assembly now, and we can start to have a look at some of the parts. So we'll go to the wheel, being probably one of the easier ones. One thing you'll notice straight up, even though in the assembly that the wheel was a grey colour, I've defined that colour and that material at the assembly level. Once we go to the parts, you'll notice that the surfaces that are drawn from the skeleton model take on the colour of the skeleton model. And this is a really good indicator just to see which are your surfaces which have been shared down through that parent-child relationship, and which features like these slots and the rounds. There's a mirror in there as well, and then this peg, which ones have been created in this part. And then when we go to look in the model tree, we can also see which features that have been built in the part. once we've got the external or the published geometry coming out of the skeleton, the way we get it into the part is this external copy geom, which is also this icon just up here. So once we go into just do an edit of that part, it's coming from an external. I've done an open, and then I went in and referenced that mouse skeleton, which was the one we looked at before. Went down the model tree to the footer, selected that wheel, published geometry parcel, and it's always good to have a good naming convention so you can quickly and easily reference, but also for someone else who's looking at your model, they can get a real understanding of the reference flow. You'll get the window here, which will show you the geometries, just to give you that visual confirmation that that's the one you want, and then you just hit OK. So if I roll that, roll back up the model tree now, we'll be able to see just that geometry that's come in. So it's fairly simple. We've just got that revolved surface. We can tell it's a surface because it shows as magenta, not as taking on the part color, certainly in Creo. But nice and simple geometry, nice and clean. We don't have all the other geometry for the mouse, so confusing the visual clarity of this part. And so now we can just get stuck in to modeling up that part. So first thing is we turn it to a solid. So you can see now that's turned grey, which was the general part color. We start doing our modeling. We've got our extrusion, and then pattern those in a rotary pattern, a reference pattern for the rounds. You got more rounds than the extrude of the peg on the axle, and then the mirror of the part. So that's how we share down that geometry from the skeleton model down through the published geometry, import through the external common geometry, and then we've got our part. So this was an example for the wheel of external geometry sharing into a part. Another way of doing it, say, is having a sub-assembly skeleton. So we're not trying to sort of keep references so higher up the model tree. We're really trying to push them down as far down the model tree as we can, just to make for really light but robust modeling. So this one, I've got a skeleton which controls the lower body sub-assembly. So in this scenario, we've got the external copy geom, which is the showing the surfaces and the curves from that top level assembly, which is fairly simple, fairly straightforward, nice clean surfaces. I then want to go do some additional part detailing for features that are going to be shared amongst parts within this lower sub-assembly. So I'm going to put in a part line between these two parts, the main or the lower body and the battery cover. This geometry doesn't need to be in that top level skeleton because it really doesn't control any of the top components, only these bottom ones. So I push that right down into that lower level. So we do a bit more modeling. I've got a little thumb grip in there, and this thumb grip goes across the part line. So this is geometry that's shared by these two parts. So similarly, like I did before at the top level, I've then got our external copy geoms for the lower and for the battery cover. So you'll see here the battery cover now has a feature defined for that little foot, for that little self-adhesive non-friction pad that goes in there. This one's only referencing the one at the back, where the lower body is only referencing the one at the front. We don't need to reference that across both parts because that feature isn't shared by both parts. Then if we come down into each sub-assembly. So the lower housing here, we've got each of the parts which have an external copy geom brought in from that lower body skeleton, and then has the defining geometry to continue those features down into those subcomponents. So they're all all where we want them to be, but they also align and correspond with the mating features on the mating parts. Come back up to the assembly, and so you can see we've now got that form geometry. Again, you see the pink surfaces which have been carried through from that very top level skeleton, just to show us and give us an indication of the data sharing down through that, or the geometry sharing down through that assembly structure and the skeleton structure. One crucial rule when doing top-down design is I never copy across or references across an assembly. So if I'm modeling in this part, I won't go and pick geometry here or references in this part. That can give us certainly some very nasty failures with circular references, where if this part falls over, the features in this part will fall over because they're relating on that parent-child relationship from that other part. You won't ever get circular references when you're using top-down design if you sort of follow nice discipline practices and only take references from the top level. If your top level skeleton falls over, then everything else will have errors, but it's only in that case. So if this one has a feature that falls over around or something, this part will remain stable. So that's, I guess, a brief overview of how we get the assembly and the subcomponents and subassemblies created and constructed. It's fantastic for these sorts of areas where you've got overmolded parts, you've got a substrate part, and you want to ensure that your overmolding tool is going to blank off nicely around these surfaces here. You want nice, good, clean part lines. And so again, we're using those common surfaces just to ensure that we're getting the best quality product at the end of the production line as we can. So that's a fantastic way to get things started, but this is where the next part is where the real value of top-down design starts to come into its own. As often happens, it's usually 5 minutes to midnight. You're wanting to send parts out to prototype or out to tooling, and marketing, or your boss or your project manager comes in and goes, "Oh, we've had some market research. It's too short. We need to make it longer." And so the advantage of this sort of reference control, the entire length of every component and the product as a whole is driven and constrained by this one sketch, and then all the features that built off this sketch we'll update. So this is currently 110. Marketing said it's too long, so we want to turn that down to 100 and make the whole unit shorter. And this can also be done for if you're doing different sizes. You have one at 110, copy a new sub-assembly across. I'm doing a backup with all your parts, and create a small part, but still keeping the same look and feel. So now I've made that change from 110 millimeters down to 100 in the skeleton. I come back to my assembly. You notice icon showing that requires regeneration. So now I just hit regenerate. So those changes are filtered down through all the skeletons into the parts through the published geometry and the external copy geometries. And there we go. We've now got a product. I can pick those correctly, which is, give or take some change, is 100 mil long. Marketing might come back and say, "Oh, actually, 100 was too short. Let's go a midway point." So we now go 105. Changes the skeleton. Come back into the top level. Do your regeneration. Filters through. And then by changing one dimension, there we go. Our size of our product changes. So that's fantastic, nice and flexible, nice and robust. What gives me confidence, though, from using this style of modelling practice is all the constraints that I've set up in between the parts in terms of these offsets of part lines. These are all locked into the parts via the assemblies to ensure that this offset will always be the same distance apart regardless of what's happening to the surface. And so I can change and flex the outer geometry and the outer surface of this quite sort of complex surface geometry, but ensure that these part lines are going to be maintained in uniform. Big advantage of that is if you you're about to send parts out for prototyping, or worse, out for tooling, and you make a change, it can save you a lot of time going in and actually checking every inch of the model to ensure that all those design intents that you've built in earlier in the piece are still captured and maintained. With this style of modelling of top-down design, you've got good confidence they are. Yes, you'll always want to go and do a quick check, but you've got good confidence that that the part lines are going to be maintained, that the surface continuity across matching faces or shared faces are going to be maintained, and that really is one of the powerful parts of top-down design, is it just gives you that real confidence in your modelling, especially when changes happen, which they always will. And yes, it's certainly served me well for the last some 25 years of my 3D CAD modelling career. So I hope you've enjoyed this presentation. Looking forward to doing more in the future, and certainly if you need any CAD modelling assistance or industrial design consulting assistance to meet your resource requirements or your project requirements, please feel free to contact me at Equip Design and Consulting, and we look forward to seeing you soon. Have a good day.